Now I am going to introduce the concept of characteristic of a ring. What does it mean? Now, if you consider a ring, suppose R be a ring, and you consider an element A, okay, then with respect to this A, you can sum off this A n times, right, which will be denoted by Na. Okay, this doesn't mean that it is a multiplication of n and A. Okay, this means that A has been n has been added n times. Okay, yeah. Okay, this n is an integer. Okay, that means suppose you take minus 1. Suppose A is so if you take suppose minus A, okay, then minus A plus minus A plus minus A and n greater than 0, okay, n times, that means n minus A. Okay, right. Okay, now if you take n is less than 0 and A belongs to R, okay, then what is Na? So Na is actually minus A plus minus A plus minus A, how many times? Mod n times. Okay, and we define 0A as 0 element. Okay, now our interest is to search for a positive integer n for which Na is going to be 0. So our search will be to get a positive integer n for which if you add A n times, that will be 0. So this is our search, and this will be for all A belongs to R. Okay, if you look at this ring, suppose you take Z, suppose you take Z5, this ring, then this contains 0 class, 1 class, 2 class, 3 class and 4 class, right. Now if you are going to add 1, so if you are going to add 1 class up to 5 times, so this is actually five 1 class, so it is 5 times. So this is 0 because this is actually 5 class. So 5 class is 0 class in Z5. Now if you take 2 class, then also if you take this 2 class and you are going to add 2 plus 5 times, then you will have 10 class, which is again 0 class. Now if you take 3 class and you add them 5 times, then it will be 15 class, and then again it is 0 class, because 5 divides 15. And if you take 4 class and if you add them 5 times, then it will be 20 class, and it is again 0 class. So therefore this 5 is a positive integer for which you can say that in Z5 5a class is 0 class, and this is true for all a class belongs to Z5, right? Okay. Now if you take Z8, for Z8 you will have 8a class equal to 0 class, for all a class belongs to Z8. Okay. So in particular in Zn you are going to have Na class equal to 0 class for all a class belongs to Zn. Okay. So these positive integers, suppose if you take Z5, so this 5, and if you take Z8 then 8, and if you take in general Zn, so n, the positive integer n, so these are called actually the characteristic of that ring. Okay. So our definition is like that. So the characteristic of R, the ring R, is defined to be the least positive integer n if it exists. Yes, if it exists. So defined to be the least positive integer n such that Na equals to 0, which will be true for every element of the ring. Okay, which will be denoted by char R. So it is your n. That is, characteristic of a ring is the least positive integer for which Na equal to 0 for all a belongs to that ring. Okay, and if it doesn't exist, if you cannot find out any least positive integer which results this property, then you can say that the ring is of characteristic 0. So if no such n exists, then R is said to be of characteristic 0. That is, characteristic R equal to 0. Okay, right? So it should be remarked that if you take a finite field, suppose in particularly that we have already discussed about Z5, Z5 is a finite field containing 5 elements. So in general, if you take any finite field, suppose ZP, P be a prime, so why it is a field? Let us prove that ZP plus dot is a field if and only if P be a prime. Now you should be recall that as I have already said before that ZP plus dot, it is a commutative ring, right? It is a commutative ring with unity which is 1 plus. Okay, and also it is a finite set. It is a finite set. Okay, so suppose you take so let ZP plus dot be a field. Okay, so our claim is that P must be prime, right? P must be prime. If not, suppose one says that no sir, P is not going to be a prime number, so it must be a composite. Suppose it is AB, that means 1 less than A less than P and 1 less than B less than P, right? Then this A and B will give you two classes. One is A class, another is B class. In between this 1 class and P class, right? So that is AB class equal to P class. Now P class must be 0 class because it is in ZP. So here A class dot B class equal to 0 class, right? Now you have already assumed that this ZP must be a field, right? ZB is a field. So being a field, this A class must have a multiplicative inverse. Now A class inverse exists, and then if you multiply this AB class, A class, B class and 0 class both sides by A class inverse, then it is 0 class and it is your B class. So here you see that this B class has been proved to be 0 class, right? B class is 0 class, but this is a contradiction because of this one, because B is less than P, so but P does not divide P, so it is a contradiction. So therefore what we have assumed that P is not a prime was false. So therefore P must be a prime. Okay. Now conversely, suppose that P is a prime, and you need to check that. So the claim is that ZB plus dot is going to be a field. That is, it is enough to check that every non-zero element of ZP has a multiplicative inverse. So for this, let A class belongs to ZP be non-zero. That is, A class not equal to 0 class. Okay. Now as you have said that, as you have assumed that P be a prime, so GCD of A comma P, this must be 1, which leads to the fact that there exist two integers x and y, so that their linear combination, that is ax plus by, must be 1. From this you can say that so ax minus 1 equal to minus py, that is p divides py, and py is actually 1 minus ax. So p divides 1 minus ax implies ax class equal to 1 class, that is a class dot x class equal to 1 class. So this proves that a class has a multiplicative inverse. Right? Because of commutativity, you can say that x class dot a class is also 1. Right? So a class has a multiplicative inverse, and this proves our claim. So therefore ZP plus dot will be a field if and only P is a prime number. Okay. And so the remark is that suppose for a finite field ZP plus dot, you can check that P a class must be 0 class. Okay, for all a class belongs to ZP, which says that characteristic of ZP must be P. On the other hand, if you look at this field Q plus dot, field of rationals, then you will see that then there exists no n for which na equal to 0, which that is characteristic of Q equal to 0. There exists no such n for which na equal to 0 for all a belongs to Q. This doesn't happen. Okay. So field of rationals has characteristic 0, but field of the finite fields where P be a prime, then the characteristic of ZP must be P. Okay. Now one observation that we can encounter if you look at an integral domain. Okay. So if suppose remark 2, this can be written as remark 1, remark 2, that suppose you take R be an integral domain. Okay, in real domain, and suppose let us assume that for a positive integer n and for a non-zero element small a belongs to R, na equal to 0. Okay. Suppose in particular for a non-zero element a, you see that na equal to 0 for this positive integer n, then what will you have? Then na is actually a plus a plus a plus n times by definition n summons. If you take a in summons, then it will give you this na. Okay. Then this A is actually A dot 1, A dot 1, A dot 1 n times. Now by distributive laws, if you take this A out, and it is 1 plus 1 n times, right? So that means it is A dot n dot 1, right? Right. So from this one you can say that, so being an integral domain where A is a non-zero element, so therefore this n dot 1 must be 0. Okay. And from this you can say that, suppose you take, so let x be any element, then this nx will be represented as x dot n dot 1. Now since n dot 1 is 0, so this is x dot 0, that is 0, and this is true for all x belongs to R, and this proves that characteristic of characteristic of R must be n. So hence in an integral domain, if you can find out for a non-zero element a positive integer n for which n equal to 0, then you can say that this integral domain will be of characteristic n. Okay. So in particular, so in general, you can prove this theorem, and I would like to end off this session with this theorem. So suppose you take R be a ring with unity 1, then R is of, then characteristic R equal to n, which is greater than 0 if and only if n be the least positive integer for which n1 equal to 0. Okay. So in a ring with unity, you need to check only the case for 1, that is, you are going to search for a least positive integer for which n1 is 0. That is enough to determine the characteristic of that ring. Why? Because of the same procedure that we have written here, this one, because every na can be written as a dot n dot 1. So R is of characteristic n if and only n be the least positive integer for which n1 is 0, right. So I would like to stop here.